Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on robust control. So, in the previous lecture we discussed these two particular examples where we saw that it was apparently beneficial to pull out a certain complicated part of a system's dynamics and separate it from the linear part of the dynamics. To be precise, the two examples we saw were one where this complicated part of the dynamics happened to be a static nonlinearity, right. So, we isolated the system into a purely linear part, a linear map characterized by G, and this static nonlinear part characterized by Q. In the second example, we took a different route, although we saw that the eventual structure still turned out to be the same. Here again, the G part of the map represented the linearized or the linear part of the system dynamics, whereas the Q part represented a dynamic but nonetheless higher order modes of the system's dynamics. So, let us go back and revisit quickly to recap and refresh our memory, right. So, here is what we had. We wanted to isolate the nonlinearity here in the first example. So, initially we started with this nonlinear system described by x dot is equal to f of x comma u, where f is not necessarily a linear function naturally, and then of course the output equation was static. So, we showed you that one way in which you could get a linear approximation of this nonlinear system is to linearize this system about some operating point or an equilibrium, right. And thereafter we saw that you have this G which is here boxed in this red color. This represented the linear part, okay, from which the nonlinearity we managed to mask somehow, right. And then we saw that this G happened to be a linear map from a set of signals like W1, W2 and U to another set of signals such as X, U and Y. Of course, in control theory we call X as the states, U as the input, Y as the output, right. And then we saw that this Q part then became a static nonlinear map from W1 and W2 to, from X and U to W1 and W2. So, it ingested the signals X and U and mapped it to W1 and W2, which were nonlinear functions of this X and U given by G and R, as you can see here, right. So, this was the first example. The second example we of course took was that of a higher order system, right, where we ignored some of the states, the higher order dynamics represented by x2. So, essentially this is x1, right. Yeah, so eventually this is x1 that we were concerned with. So, we said that we choose to ignore this x2 because it is as if we are only concerned with those modes of the system which are probably the dominant modes, as you might have heard in a conventional undergraduate course, right. The dominant modes means the slower modes, the ones corresponding to which the poles or the eigenvalues have smaller real parts in the absolute sense, okay, closer to the imaginary axis, all right. And then we saw that, well, this first part here that you see, this part here, right, this we can represent in the same fashion as we did earlier, which is that G, which is a mapping from W1, W2 and U leading to an output which is spat out by it given by x1, u and y, right. On the other hand, Q was also a mapping from x1 and u to w1 and w2. The one significant difference now being that this x2 dot is also part of this Q. So, unlike the earlier case where Q happened to be a static map, here Q actually has some dynamics. Now, as I said, of course, if you consider these dynamics to be very fast, then for practical purposes you might also assume them to be static, yeah, because after all, what is a static system? Something whose dynamics is too fast for us to even consider in our formulation of the problem, right. So, in general here in this second formulation, Q is not a static nonlinear formulation, but rather a dynamic one. But nonetheless, you see that the same structure resulted once again, right. The idea behind these discussions is that, well, a plethora of different problems can be cast or can be formulated in this GQ form, where you have this G capturing a linear map and Q capturing the more complicated parts. Now, you might naturally question, hang on, after all this Q is still very complicated. Maybe we have managed to pull it out of the G, but we understand G well enough, remember. But when you have to analyze this system at the end of the day, it does not just suffice that you understand G well enough, you still have to understand Q well enough. So, after all, what benefit can we reap from managing to pull out this Q and separate it from this G, whether this Q represents the higher order dynamics or whether it represents a static nonlinear part? How does it even help? And here is the answer to that question. So, what we do is, look, this Q is after all a map, okay, or a function. What we now try to do is, we replace Q with a set of linear maps, okay. Sounds pretty unconventional at this stage probably. So, let me formalize that slightly. So, you consider a set delta, okay. This is a set delta, right. So, this delta is a collection of maybe several deltas, small, written like this, yeah. I do not know how many deltas, maybe delta k, okay. Now, what is so special about this delta? It turns out that what we want is this delta should be able to adequately replace or substitute for this Q. What is so good about this delta? Well, these deltas are each member of this set big delta is individually a linear map. So, this delta 1 is a linear map, delta 2 is a linear map, so on till this delta k, yeah, this is also a linear map. And linear maps we understand well enough, right. So, although this Q might be a very complicated object to handle, given one of these linear maps, we would not be so unhappy with that, right, because now we have after all the interconnection of two linear maps. G is a linear map, delta is a linear map. But the problem is, if you are trying to substitute a nonlinear map by a linear map, then one linear map will not suffice. After all, it is because the system is nonlinear that it cannot be just exactly substituted by a linear map. So, what is this specialty? Why are we choosing this set? It is precisely where this relation will come in instead of a mapping. What do I mean by a relation instead of a mapping? So, this is how we propose to go about it. Now, suppose we have a bunch of signals, say P1, P2 dot 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 till I do not know, maybe quite a number of signals, right, maybe Pk, yeah, I mean, yeah, this is not nothing to do with this earlier k, maybe I can replace this as L, whatever. So, some bunch of signals, suppose we have a bunch of these signals, and for each of these signals we know that Q1 is equal to Q acting on P1, Q2 is equal to Q acting on P2, so on till Q acting on Pj gives us Qj, right. So, maybe this nonlinear system we may not be able to completely capture its behavior, but in so far as certain signals are concerned, certain signals of our interest. Okay. So, here we have to sort of bring the problem down to a simplified stage. We cannot say that we are going to capture this behavior of this Q for every possible signal. Yeah, we'll have to be, we'll have to concede a little ground there. We'll say, okay, we considered a class of signals, maybe a set of signals maybe, for which we want to understand what this Q does to such signals. Yeah. So, when this operator Q or this map Q, this nonlinear map or the static or dynamic, whatever it is, this map Q acts on some of these signals, what does it spit out? So, this small q1, small q2, yeah, can we at least infer about these things? If we can, then here is what we do. We say the set delta, remember this big delta I am referring to, right? The set delta is such that for any pi such that q pi is equal to small qi, we have some delta j belonging to delta satisfying the condition that delta j, if this would have acted on pi, it would have also given us qi. Seems a pretty long winded sentence now. Let me try to go a little slowly over this and try to explain what I am saying here. Look, you have this complicated looking map, this nonlinear map, maybe static or dynamic, which is captured by this Q, right. What is this Q doing? This Q, when it acts on a bunch of signals, maybe some signals of my interest, I cannot say every possible signal, that will be a very difficult problem indeed. So, if it acts on a bunch of these signals, it definitely spits out some other signal, maybe qi. When it acts on pi, it spits out a signal qi. Now, I am saying that maybe I cannot capture the behavior of Q for all these possible signals through a single linear map. If a single linear map were to be able to capture the behavior of this operator capital Q, then the operator capital Q would have been a linear map, right. Because obviously, why would it be non-linear? If a single linear map can capture what Q does to every signal, then that linear map would be identical with Q, and then Q would cease to be a non-linear map, right. So, the only difficulty arises because Q is a non-linear map. So, it is impossible to have a single delta j, right, which captures all the behavior of Q against all possible inputs pi that you can give to it. But what we are saying is, it may not be that a single delta captures the behavior, but at least for every possible pi. So, it is like a game of cards, right. We are playing a game of cards. You throw me a signal pi, yeah. What I have to do is, yeah, you throw me a signal pi, I have to check what would this operator Q have done to pi. So, I check that. I have the tools to check that. I check and find out that the signal pi that you have given me, if the operator Q acted on it, it would have given me the signal qi at its output. Now, my job is to play my card. What is my card? You played the card of pi, my job is to play the card of delta j. I have to capture some linear map, yeah, some linear map which would have satisfied this property. So, you keep playing one card after another, that is to say, you give me one pi after another, p1, p2, p3, p4, p5, and for every such p that you give me, if I can always come up with some delta 1, delta 2, delta 3, delta 4, delta j, right, then I string together all of these deltas and combine them into a single set, that is this delta, yeah, then I would have won the game. In other words, I have managed to replace, so that way Q can be replaced So, let me put below Q that Q is a map, yeah, can be replaced by a relation, yeah. So, this is a set, remember, that is why it is a little unconventional, okay. We are replacing whatever Q does, the effect of that nonlinear mapping, that static on dynamic nonlinear mapping, we are replacing it by not just a single linear operation, but a bunch of these linear operations or linear maps, yeah. So, that is why it is no longer a map, but a relation as opposed to a map. So, now this figure that we had drawn earlier, it would look a little different. Recall that in the previous lecture this is the figure we were dealing with. Now my job is that I should be able to replace this with this set delta. So, then it turns out that no matter whatever is spat out by this G here, there exists some member in this delta in this set such that I have the tool to generate the exact same output that Q would have generated over here. And then remember that because each of these maps in this set delta is linear, so I am going to study a bunch of behaviors instead of a single behavior, okay. Let me delineate that a bit. So, now I am dealing with a family of operators or a family of maps. Remember, with this G, if I consider delta 1, that is one of the members of this set big delta, I get one linear map. If I consider delta 2, I get another linear map. If I consider delta 3, I get another linear map, right. So, for all of these deltas, if I can assure that my system behaves in a desirable fashion, then I can also assure myself that, well, my system would also behave in the desired fashion with the actual Q, provided of course that the signals that I am feeding to it are this PJs only. Yeah, I cannot expect to model or capture the behavior of Q through deltas for a certain bunch of signals and then apply a totally different signal and expect the behavior to be there. It will not be there, right? It will not be captured by these deltas, right. So, what is the benefit of this? Remember, for every time you pick a single member from this set big delta, you are basically picking out a linear map. So, this G is already linear and whatever is coming here is also linear. So, each of these is a linear system. So, you capture this family of linear systems, and for each of these linear systems in the family, if your performance is satisfactory, yeah, then your performance will also be satisfactory for the original system which is captured by Q. And that is essentially the idea of robust control. That is why we look for a family of plants. Something I want you to be warned about at this point, looking at this you might feel that here this is enumerated, right. So, this is delta 1, delta 2, delta L. So, it might seem like this is a countable set. Remember that this I have done for simplification, but this is not necessarily a countable set. This I have done for easier visualization. Here of course, it is a countable set, it has got exactly L members. So, it might be a continuum, right. So, the idea is have a complicated structure, pull it out from the linear part, the simplified linear part, yeah, and then try to approximate it using a family of linear maps, and then check whether you get the desired behavior for the whole family of these linear maps that you managed to approximate this nonlinearity or this complicated dynamics by. If you manage to do that, you would have satisfied the robust performance and robust stability criteria and requirements, right. So, just if you give it a moment's thought, what I am now going to say will make a lot more sense. So, here it goes. So, look at this set here. I am going to explain this of course in a little detail. So, this set is a set of signal pairs PQ such that Q is given by this operator Q acting on the signal P. So, this is one set. So, this is a set of all such signal pairs which are input output pairs, right. You give P as an input to this operator big Q and you get small q as the output. So, all such pairs of signals I capture in this S1, and then I have this set S2. How is S2 defined? S2 is also likewise a set of two tuples of signals, pairs of signals, ordered pairs, such that there exists, very important, some delta belonging to big delta. Remember, I have gotten rid of the subscript here, because as I have already told you that this subscript might give you the false notion that it is enumerable or that it is countable. But I have told you already that this set is not necessarily countable. This was just as a toy example I wanted to explain to you, yeah, because it is always easier to map with the set of integers. But in general, shortly we will take another example where you will see that what I mean by the set not being countable. Okay. Anyway, let us get back to the problem on hand. So, this is a set S2, which is also a set of signal pairs. What property does this signal pair satisfy? So, this is a set of PQ such that there exists some delta in the set big delta satisfying the condition that Q is equal to this linear map delta acting on P. Okay. But the big claim that I am going to make is that S1 is actually a subset of S2 if delta is not a singleton set. Again, you might be a little wary of this, what I mean by all of this, right? Very simple. It might seem a little daunting to think of at first, but here is what it means. Now, suppose this delta is not a singleton set. What do you mean by singleton set? A singleton set means a set that has only one element. A set that has no elements is an empty set. So, the next best thing to an empty set is a singleton set. Maybe a set of points, maybe a set of points that has only one point is a singleton set. A set of apples that has only one apple is a singleton set. Yeah. So, similarly, a set of such linear maps which has exactly one linear map in it, yeah, is a singleton set. Now, clearly, if this set delta that I have defined here like this, as you see before yourself on the screen, if this set delta has to be a singleton, then I put it to you that the map Q has to be linear, because then this one delta itself, this one linear map is good enough to capture this entire nonlinear map. So, if a linear map captures the behavior of a nonlinear map, it seems very counterintuitive, no? After all, if for every signal, whatever a nonlinear map does to that signal is exactly the same as what a linear map does to that signal, then why is it nonlinear in the first place after all, right? It is just a linear map. So, it is non-trivial to say that the set delta, big delta, should contain at least two elements, if not more. It can contain uncountably infinite number of elements, as again we will see later. But at least for now you agree that this set delta, big delta, contains at least more than one element. If it contains at least more than one element, then the claim that I am making here, is the following, that this set S1 is a strictly proper subset of S2. So, it is basically a smaller set. So, S2 contains definitely more elements, strictly more elements, not even equal, strictly more elements than S1. What does that mean? What is a typical element in set S1 like? It is a pair of signals, such that the first signal when acted upon by Q yields the second signal. What is the set S2 like? It is again a pair of signals. Of course, you cannot compare two sets unless they have similar type of objects in them, right? So, S2 is also a two tuple of signals, ordered pair of signals, such that for every P that you give to it, yeah, there exists some delta which leads to that same Q. Okay. So, why am I saying that it is obvious that this is going to be a subset? Think about it. Just think about it. What does it mean to say that S1 is completely included by the set S2? Remember, if a particular delta were to act on all possible P's that you give it, yeah, it will lead to different Q's, all right. So, for example, here is a bunch of inputs that you give it P1, P2 dot dot dot, let us say Pk, and you pass all of them through say one delta, and you get delta P1, delta P2, likewise till delta Pk. Similarly, you pass this through say delta bar, right. So, delta, delta bar, maybe delta hat, they all belong to this big delta. Okay. So, let me not just use subscripts, because as I said these are not necessarily countable. So, this leads to the set delta bar P1, delta bar P2, likewise till delta bar Pk. Similarly, when these are acted upon by delta hat, let us say, so I am just taking 3 elements for the timing, there can be an infinite number of elements in big delta, right. So, this will give you delta hat P1, delta hat P2 and delta hat Pk. Now, remember each of these is a linear map, right, this delta, delta bar and delta hat, these are all linear maps. But when I operate the actual function q, the actual nonlinearity on q, I will get q P1, q P2, q Pk likewise. Now, remember what does it mean? The way I have constructed this set delta, a typical way in which this can proceed is, here is what happens. So, maybe this q P1 is equal to delta P1, but q P2 is equal to delta bar P2 and q Pk is equal to delta hat Pk, right. So, all possible input output pairs are appearing. You take the possible inputs from here and you take the possible outputs from all of these sets, it could be any one of these. So, Qp, yeah, when you hit this signals P1, P2, P3 till Pk with the original nonlinear complicated dynamics Q or the complicated map Q, you are sure to end up with some of these signals. So, maybe this signal, when you hit P1 with it you get this signal, when you hit it with P2 you probably get this signal, when you hit it with when you hit Pk with it Q, you probably get this signal. So, the way I have constructed this set big delta, I am guaranteed that there exists some delta in big delta, maybe delta bar, maybe delta hat, such that which gives you equality. But the overall set of all behaviors that are contained in this big delta set is a much wider class of behaviors, no? Because when you hit P1 with Q, you only end up with getting one of these. But if you hit P1 with all possible members in this set big delta, you could have gotten delta P1, you could have gotten delta bar P1, you could have gotten delta hat P1, right. Similarly, when you hit P2 with every element in this set big delta, you could have gotten this delta P2, you could have gotten delta bar P2, you could have gotten delta hat P2. So, this set big delta gives you many more options. You could have paired up P1 with delta P1, yeah, this could have been one pair. You could have gotten P1 with delta bar P1, yeah, you could have gotten P1 with delta hat P1, yeah. These all fellows, all of these behaviors are contained, right, all of these behaviors are contained here when you consider the set or the mapping Q to be approximated by the set big delta. However, Q is only going to pick up any one of them. So, naturally the set of all possible input output pairs that are contained in set S1 is a subset of the behaviors or the input output pairs that are contained in S2, right. So, I hope that that point is at least clear, and this is very interesting because now if any property holds for all possible input output pairs in the set S2, listen very carefully. if any property holds for all possible input output pairs in S2, it must therefore also be true of every possible input output pair in S1, because after all S1 is a subset of S2, right. Think of it in this way, I have one set which is contained in another set. So, let us say I take a set of all citrus fruits, yeah. So, citrus fruits means lemons are included there, oranges are included there, the musambis are included there, right, all these sort of lemon like fruits, yeah. And let us say I characterize them by saying they are always going to be a little, they are rich in vitamin C. So, if the set of all citrus fruits are rich in vitamin C, then the set of oranges, which is also a part of the set of citrus fruits, is also going to be rich in vitamin C. So, therefore, the moment you agree that this set S1 is contained in the set S2, any property that holds for the set S2 must by default be true for the set S1, but the converse is not necessarily true. S1 might be a very special kind of a subset of S2. So, some property that may be true for S1 need not be true for S2. Again, to give that orange and citrus fruit analogy, yeah, you can say that oranges are primarily of two kinds of varieties in India. Indian oranges are of two kinds of varieties. Let us say this, you take the set of Indian oranges as a subset of the set of citrus fruits, and you say there are mainly of two varieties that are most famous. One is the Darjeeling variety, the other is the Nagpur variety, right. But that does not mean that you take any citrus fruit that is famous in India and you say every citrus fruit in India can be primarily of two varieties, the Darjeeling variety and the Nagpur variety, right. So, what is true of a subset need not be true of the whole set, but what is true of the whole set must be also true of the subset. So, therein lies the conservatism that we are incorporating in this, okay. So, if we are saying that something is true of S2, it must also be true of S1, right. So, the more the conservatism that you incorporate in this, in cooking up this set S2, yeah, the more conservative you are being. So, you are imposing more strict conditions on this. Now, unfortunately, this is something that always comes with it, right, because now remember the actual Q, as you can see from this one, the actual Q will only be for a signal P1, it will either give you this one or give you this one or give you this one. But when you are considering the entire set of all possible deltas as your linear maps that can replace Q, then you are trying to design for the worst case or maybe for all of these cases. So, you are ending up being more conservative, okay. So, just for example, if you give the signal P1, yeah, and then delta of P1 is very badly behaved, delta bar of P1 is reasonably behaved and delta hat of P1 is very well behaved, alright. And when you pass P1 through Q, you manage to get this delta hat which is actually very well behaved, right. So, as far as the response to P1 is concerned for Q, for this operator Q or the nonlinearity Q, you would not have been so worried if you had dealt with the original Q. But now that you are replacing this with the whole set of possible linear maps, you have to also account for the fact that, well, this delta of P1 is very badly behaved. So, you will have to design a controller to tackle for this, even though for the actual Q, this particular behavior of this delta of P1 matters not, right. So, that is the sense in which you will end up becoming more conservative. So, that is the price you pay. On the one hand, you simplify the nonlinear or complicated dynamics into a much more simplified dynamics, which is all well and good, but on the other hand, you end up paying the price like this, okay. The price being that you end up being very conservative in your design, you end up keeping a lot of factor of safety, a lot of margin, more margin than is probably warranted or necessary in your design, okay. So, although at this point it might appear like this is very abstract and what not, and maybe we are still not getting very hands on mathematical with this. So, we will get into that, but before that, as I said, because this is a graduate level elective course, it will require a bit of mathematical sophistication. So, before we jump into those things, maybe I feel it is worth our while to sort of have a quick refresher of some notions. So, we will have to draw heavily on ideas of control theory, modern control theory especially, and more importantly, much before that, ideas like those which we borrow from linear algebra, matrix theory, maybe sometimes convex optimization, linear matrix inequalities and so on. So over this lecture and the next few lectures, we will try to give you some insights about those fundamental notions. So it might seem like a bit of a more of a maths class than a control theory class for that matter, but we will have to build those foundations so that whatever is to follow after that seems to flow pretty smoothly. So with this sort of a motivation, I hope that at least you understand what we are going to try and do in this robust control course. At the heart of it will be, we try to sort of get the essence of a simplified linearized dynamics of a system and a set valued mapping, yeah, a set of linear maps, yeah, which are an adequate replacement for the more complicated potentially nonlinear map, and then we try to address this overall system where this G and delta, yeah, captures our behavior of GQ adequately. The two main problems we shall be dealing with, are one of stabilization, yeah, and the second, and this is a problem of disturbance or noise rejection, which is obviously something to do with so called performance, yeah. So even in the course of this diagram that we have drawn, you will be able to appreciate what we are trying to do here. Here is what it is, right. So here is this delta, okay. Here is some output, here is some input, yeah, and we will try to design a controller here. So this is our controller. What we are going to try and do is this G delta form that we see before us here. This is basically the plant with the perturbation, with all possible uncertainties, and this controller K is supposed to act in a manner that will serve two purposes. One, to ensure that this overall system is stable. So this controller K has to be a stabilizing controller. Now of course we will refine our definition and describe stability in further details. Yeah, there are notions like internal stability which we will encounter pretty often, closely related to what you are familiar with, asymptotic stability, that is in an undergrad control course maybe. At the same time, recall that typically these type of external signals that we are talking about here, the ones that are coming exogenously here, these are typically some of the undesirable signals that we show here. So what we want is that overall this map, let us say this map S of G delta K should be such that it is a map from, let us say this is del W and this is Z, it is a map from W to Z, yeah. If we want to find out this map from W to Z, then we will say that we want this S delta, this magnitude, to be minimum. What that means is that any external disturbance or any undesirable signal should not be amplified but attenuated. The effect of any undesirable external signal that is coming into this system should be attenuated at the output. So typically, something that you are very familiar with in an undergraduate course, what sort of a signal do you want to see the influence of which you want to basically eliminate. So in that case we typically take this Z that you see here. This Z is typically like the steady state error signal, right. So you take the Y and you take the reference, so Y minus R is your error. So your Z could be that error signal, right. So Y minus R should be minimized subject to the application of disturbances and noises at different parts of the closed loop. So all those signals like the disturbance and noise, they would be stacked up as a vector in W, and the Z would potentially contain signals like the error, the steady state error signals, the error between the reference and the output, right. So, we want to minimize these effects, right, the effects of these disturbances and noises on the error, so that we get perfect tracking. That is what the tracking problem is, right. So, depending on what problem you are tackling, you will choose your W and Z accordingly, alright. So, obviously, if you choose your Z to be just the output, then you might be wondering why do we want to minimize the effect of this, right. After all, we want the output to be exactly equal to the reference. So, if you choose your Z to be the output and your W to be the reference, then it makes no sense to say that, well, I want this mod of S to be, or this magnitude of this S to be minimized, right, because you want perfect unity gain there, isn't it? You want the reference to be perfectly tracked by the output. So, the way we pose our robust control problem is such that the W's are always chosen as undesirable signals whose effects we do not want to see in what? In the signals that we want to keep small. So, typically the Z will be a vector of all those signals which we want to be small, such as the error signals. So, it is not the absolute value of the output, but the Z would contain signals like R minus Y, the difference between the reference and the output. Okay, that is how we pose the problem. Okay. So, later on when we take more examples, as we go further down the course, these things will become clearer, but yeah, at this point if you had felt that this is a rather mystifying thing, yeah, it appears rather counterintuitive as to why we want to minimize this. I hope that that explanation that I have just given you now, that clarifies matters for you, right. So, do not think of the Z as typically the output that you see in a closed loop diagram in your control theory course at an undergrad level, right. The Z would probably contain the error signals, and this is how we pose. So, the robust control problem, as we shall see, the controller design problem will be one of minimizing this. Yeah. What do we minimize? What do we mean by this magnitude? We will need to go into more details of this. We will need to understand the ideas such as norms of systems and signals. Yeah. What do we mean by gains and amplifications? Of course, at the CISO level you understand that at steady state you talk about things like Bode plots and their magnitude functions and so on and so forth. But for a multivariable case, what are after all these so called gains, right? Yeah. So, these are exactly the sort of mathematical objects we will study. Unfortunately, or maybe fortunately, whatever way you look at it, it is your perspective. Before we embark on these things, we have to get a little formal, which is why, just as I mentioned a while back, we will have to understand some of the more nitty-gritties of the mathematical details. So, let us, in whatever times left in today's lecture, embark on this journey already. So, we will try to see some fundamental ideas of linear algebra, and subsequently, as I said, we will study some fundamental revisit maybe if you have already done these courses, revisit some ideas from matrix theory, convex optimization, so on and so forth. Maybe a little bit of topology, maybe little bit, not too much details. So, again, if this appears a little too heavy on mathematics, please be assured that sooner than later we shall get it back on track with this problem that I have promised to solve for you by the time we are done with this. Okay. So, bear with me, because even if you are very familiar, I suppose that revisiting these details will not be a waste of our time, at least, right. So, linear algebra, at the heart of linear algebra, we first try to understand this object called a vector space, right. So, what is a vector space? A vector space would comprise a set V, a field F, an operation called vector addition, and another operation called scalar multiplication. And now, if I go into a definition of field and all that, it will be a little too abstract. For our case, you might just forget about a formal definition of field. We will invariably choose this field to be either the set of complex numbers or the set of real numbers. So, these are things you really understand even without getting into the mathematical nitty-gritties. Okay. So, let us just say that for us the field will be either the set of complex numbers or the set of real numbers. Why they are fields, why they satisfy the definition of fields, in order to understand that we have to get into what fields are all about, right. So, let us just agree to not dig deeper into this definition of a field here, because otherwise we will probably end up a long time just discussing tidbits of linear algebra. That is not the idea here. We want to go quickly over this without appearing to be too rushed about it. Okay. So, what is this set V after all? Okay. This could be a set of any sort of objects, it could be functions, yeah, it could be what you understand in to be conventionally as vectors, yeah, maybe just n tuples, right, in the Euclidean space. That is the most common example of a vector that you can think of. So, what are these ideas? So, a vector space typically satisfies the following properties, and again you will have to bear with me here. So, suppose you have V1 and V2, two members that belong to this set V, yeah, then it implies that V1 plus V2 also belongs to this set V. So, this is what we call as closed under vector addition. Okay? Right, that is the first property. The second property, suppose you have V, let us not take V1, suppose you have V belonging to the vector space V and alpha belonging to the field, which as I said in our case will be either the complex field or the real field, right. Then we have that alpha times V, the product, the scalar multiplication will also belong to the set V. So, this is called closed under scalar multiplication. All right. Third property, if you have V1, V2, V3 belonging to the vector space V, then you have V1 plus V2, if you add this first and then you add it with V3, it is going to be the same as if you take V1 out separately and you add V2 and V3. So, this is the property that we call associativity, right, associativity of vector addition, all right, associativity. Next you have V1 and V2 belonging to the vector space, belonging to the set V, then V1 plus V2 is equal to V2 plus V1. So, this is again the property that we call as commutativity, commutativity with respect to again vector addition, all right. So, what have we here? We have closure under vector addition, we have closure under scalar multiplication, we have associativity of vector addition, we have commutativity of vector addition. Very important, for every V that belongs to this set V, there exists minus V such that V plus minus V is equal to the 0, or maybe I should actually have introduced the other property. So, there exists 0 belonging to the vector space V such that V plus 0 is equal to V for all V belonging to the set V. So, this is basically the existence of additive identity. Okay. So, I got the order reversed. So, this is the existence of additive identity. So, that is the 0. Do not read of this as a 0 that you understand it to be, right, depends on the addition operation that you have defined. Okay. So, just to sort of explain this, this is algebra that we are talking about, these are symbols, these are not necessarily the number 0. Okay. So, it totally is a function of what sort of an addition operation you are defining on this vector space. Okay. Accordingly, this 0 gets defined. So, do not, in most cases whatever we will encounter, you will probably see that this 0 is exactly the type of 0 that you understand, but it need not necessarily be so. Yeah, it is just the additive identity. So, it is that element which when you add to your element, any element in the set V, you get back the same element. That is the additive identity. Now, once we have defined this additive identity, then we say this existence of additive inverse. So, remember this additive identity is basically unique. Yeah. So, for every vector V, small v that you choose in this set big V, yeah, there is this unique additive identity which when added to that member in that set V gives you back the same member. Okay. Because what is this additive inverse? It is that element in the set big V which when added to the element small v gives you back the additive identity. Okay. That is how we define the additive inverse. Okay. Just take the simple examples, right, just n tuples of numbers, maybe a one tuple of a number. So, the additive inverse of 2 is minus 2 in the conventional sense of addition, yeah, the additive inverse of 3 is minus 3, but the additive identity for every one of them is just 0, right. So, the additive identity is unique, but the additive inverse is obviously different for different elements, but nonetheless for every element there exists some additive inverse, yeah, that is the important bit. So, what have we here? We have closure with respect to vector addition, we have associativity with respect to vector addition, we have commutativity with respect to vector addition, we have existence of additive identity with respect to vector addition, and we have existence of additive inverse with respect to vector addition. Sometimes again just good to know, there is a term in algebra, we call this like it is an abelian group with respect to vector addition. Okay. Does not matter if you forget it, it is more important to know what these properties are rather than just know some names of these things, right. At least for this course it is not that important. Okay. Now, there are some other additional properties too, particularly with respect to the scalar multiplication. Yeah. So, what are the other properties? There exists a multiplicative identity, okay, and this is also going to be unique, which belongs to the set, the field F, such that when you multiply, when you do a scalar multiplication with this element of the field and any v is equal to, it gives you back the same vector v for all v in the set V. So, this is basically multiplicative identity. Okay. So, existence of multiplicative identity. Okay. So, what have we seen? With respect to vector addition, we have seen 5 properties. With respect to multiplication, scalar multiplication, what properties have we seen? We have only seen so far the closure under scalar multiplication. Now, we are seeing the existence of a multiplicative identity with respect to this. Okay. Finally, we see for alpha, beta belonging to this field, again this field will always be either complex numbers or real numbers, and V belonging to the vector space V, we have alpha times beta V is equal to alpha beta times V. Yeah. So, whether you multiply those two scalars first like you have done here and then take the scalar multiplication. So, remember this multiplication here is happening in the field and this multiplication is the scalar multiplication that we have defined for this vector space. On the other hand here, this is basically a first multiplication that is happening like we have defined here. So, this is a very subtle point, it might seem like this is some funny rubbish, but it really is not. Okay. Remember here this multiplication, let me mark it with a different color. So, remember that this multiplication is basically a multiplication that is happening in the field. On the other hand, the one marked in blue is basically the multiplication, the scalar multiplication that we have defined here. Whereas here, this scalar multiplication is also happening in the field and you get back something because of the closure under scalar multiplication, this fellow also belongs to V, and again this multiplication is also happening again So, these are this on the left hand side what you have is two successive scalar multiplications. On the right hand side what you have is one multiplication among two members in the field and then a scalar multiplication. Yeah. So, it is not a very trivial thing if you think about it slightly, right. It depends on the way multiplications are defined in the field and multiplications are defined in the scalar multiplication sense. Okay. So, this is again, as you can see, the associativity property here at play, right. So, what have we defined here? We have seen closure with respect to these two operations. We have seen associativity, commutativity, existence of additive identity and existence of additive inverse with respect to addition, that is, right. And now with respect to multiplication we have seen the existence of multiplicative identity and associativity. Finally, there are two properties that will actually involve an amalgamation of both these properties, both these operations, that is the additive identity and the additive addition, vector addition and the scalar multiplication, right. So, what are those? So, I will call them distributivity 1 and distributivity 2. Okay. So, what I am saying is in distributivity 1, suppose you have alpha as part of the field and V1, V2 belonging to the set V, the vector space that is, yeah, we have that alpha times scalar multiplication V1 plus V2, yeah, is going to be nothing but alpha times V1 plus alpha times V2. Again remember, this is not very trivial. What we are saying is this addition is the vector addition that we have defined, right. Let me use a different color, otherwise it looks like a plus minus that you might mistake it for. Yeah, so this is some addition that is happening in the vector space, the vector addition. So, whether you take these two fellows first and add them in the sense of the vector addition and then you take the scalar product like we have defined, or you take each of those individual elements, perform the scalar multiplication like we have defined and then add them in the sense of vector addition like we have defined, it will give you the same thing. So, that is the first distributivity property. What is the second distributivity property? The second distributivity property is, now this time you have two members from the field. Suppose you have alpha 1 and alpha 2 which are members of the field, and you have one vector which belongs to the set V. Then what you can do is you can write alpha 1 plus alpha 2 and take the scalar multiplication of this with V. It will be exactly the same as taking the scalar multiplication of alpha 1 with V and then adding it with the scalar multiplication of alpha 2 with V. Again, because we think mostly in terms of objects that we are familiar with, these all seem very trivial and obvious, but it is far from trivial. If you just cast your attention a bit carefully on this, you will notice the subtlety here. Okay. Note that this addition here, right, this is the addition that is happening over the field, whereas this is the scalar multiplication that is happening between an object in the field and an object in the set V. But here notice that this addition is basically the addition that we have defined in the vector space V. Okay. So, although we are using the same symbol plus on both sides, they are not really the same operation. Okay. So, even though it seems like just some funny way of writing known things, they actually carry some different meaning. Okay. Here of course, this multiplication is again happening as the scalar multiplication, but this addition crucially is basically the addition that we have defined between two objects in the set V, whereas this addition is basically the addition that is happening between two objects in the set F, which in our case is either the set of complex numbers or the set of real numbers. Okay. So, any such objects, this set V along with the field F and two operations, those of vector addition and scalar multiplication, which satisfy these properties that I have just mentioned, yeah, that becomes a vector space. So, in short, when everything is understood implicitly, like what the addition is, what the multiplication, scalar multiplication is and what the field is, we typically say that V is a vector space over F. Of course, in our case F is either C or R, complex numbers or real numbers. Okay. So, in short, we just say that V is a vector space. This is what a vector space is, and then what is a subspace? The next important notion. So, suppose you understand what subsets are. Suppose V1 is a subset of V and satisfies the properties or inherits all the properties of V together with of the parent vector space V, then V is, so V1 is a not just a subset, because remember when we just say this just means it is a subset. Okay. A subset is not necessarily a subspace, right. It will only become a subspace if it satisfies all the properties of the vector space. So, if a subspace is inherently also a vector space in its own right, and also it will inherit, remember you cannot have that V has one particular definition for a scalar multiplication and vector addition, and V1, although the members of V1 are subsets of the members of V, yeah. So, V1 is a subset of V, but if you define your scalar multiplication and addition differently over the set V1, then it no longer remains a subspace of V. Okay. So, it must inherit the same operations, exactly the same operations that are defined over V. The same scalar multiplication and vector addition, it inherits from V, it is a subset of V, and it satisfies the properties of being a vector space in its own right, subject to those operations that it has inherited from the parent space. If all these are true, then V1 is not just a subset of V, but V1 is also a subspace of V. Okay. So, that is the important bit. Quite often we will deal with many important subspaces throughout our course, right. Just to give you some perspective, these are not just arbitrary abstract objects that we are studying just for the sake of it. Okay. These will be very, very important in our studies going forward with this course on robust control, right. So, please bear in mind that these are not just some idle interests that we are satisfying here. Okay. So, with those definitions that we have introduced of vector space and vector subspace, in the next lecture we shall carry on forward with this and explore some other ideas such as what is a span. Okay. We will see some examples of subspaces, okay, such as a span. Yeah, then we will see in light of the span we will see ideas like linear combinations, linear independence, dimension, basis, yeah, and then we will get into linear maps, because remember what we are trying to do is we are trying to approximate complicated nonlinear map using linear maps, right. So, wouldn't it be nice if we can have a characterization of linear maps at least over what we will call finite dimensional subspaces, right. So, we will see what those linear maps can be characterized by, and that will be very interesting, and it will involve an understanding of these notions of linear algebra that we are laying out before you right now, that we have already started to lay out. Then we will encounter some interesting results, some important results in linear algebra like the rank nullity theorem, yeah, and we will see what the image is, what the kernel is of a linear map, right, and we will maybe put an end for the time being to our study of linear algebra there, and then we will study matrices, and we will see why we will study matrices, because it will turn out that these linear maps over finite dimensional spaces turn out to be nothing but matrices at the end of the day, right. So, that is some beautiful realization we will see in over the next 1 or 2 lectures, yeah, and hopefully pretty soon we will be back to dealing with the state space representation of systems that you are so familiar with and probably getting a little more eager to get started with. Okay. So, till the next lecture, do take very good care of yourselves. Thank you.